point tree examples. So first, let's take some sets and check some relationships. So in question number 1, we have the set given by the elements 1, 2, 3 and the elements x, y, z for the set B. We want to know if we have relationships here or not. So for number 1, we have the relationship 1x, 2y. Indeed, we have things that are going from the set A to the set B. And that's pretty much the requirement for a relationship to work. So indeed, yeah, these are order pairs from the first entry in A, the second entry in B. So this is a relationship. So the answer is true here, yes. For number 2, notice that we have 1 going to X, 2 going to X, and 3 going to C. This is still a relationship. Doesn't matter that we're going to the same place with different elements, that's fine. Number 3, though, is not a relationship. And the problem is that it has the sets backwards. It has B to A. And so that doesn't match up the order of the relationship. We need that the first entry is from A, that the second entry is from B. Now, R4 is empty. In empty, it is a valid relationship, although it is a subset of A times B of Cartesian product, so we have no issue with this. Now, moving on, question number 2, we want to consider a relationship, and this time we're being given a condition for that relationship. So we have A being 2, 3, 4, B being 6, 8, 10, and we want to define the relationship from A to B as the xy pairs so that y over x is an integer. So the first question is 2 related to 6? And the answer in this case is yes, because notice that this should be x and this should be y. And according to this relationship condition, this will mean that 6 divided by 2, which is 3, is an integer. Indeed, 3 is an integer, so that's fine. So this is a relationship. Now, is 3 related with 8? And the answer is no. And the reason, of course, is because A over 3 does not belong to the integers. So because this is not the case, then it's not going to belong to the relationship. Is the pair 4, 8 going to work in the relationship? Yes, because this will be 8 divided by 4 is 2, and that indeed belongs into the integers. So this pairs belongs to the integers. So now from all the possible pairs that we can write in here, let's write the relationship. So we can go with 2 with 6, 2 with 8, 2 with 10. Since all of them, the ratio is going to be an integer. Now with 3, notice that 3 with 6 is going to work. 3 with 8 is not going to work. And 3 with 10 is not going to work either. Now with 4, 4 with 6 is not going to work. 4 with 8 will work. And 4 with 10 will not work. So this is the extent of the relationship. Now, if we're going to do like an arrow diagram for this, then we can pretty much write the elements 2, 3, 4 here. And then we can do here 6, 8, 10. And then we can do 2 is going to each of them in this direction. And we have that 3 is going to 6. And we got that 4 is going to 8. So this will be the arrow diagram for that. Now, question number 3 talks about different thing. It talks about functions. Remember, functions are very specific relationship. They have very specific conditions. So given that the domain is 1, 2, 3, 4, and B is ABC, let's determine if these are functions or explain why not. So for the first one, yes, this is a function. You're sending 1 to A, 2 to B, 3 to C, and 4 to A, which is fine. Every input has one output. So this is a yes. Now, 1 to A, 2 to A, 3 to A is not a function. And the problem why it's not a function is because 4 belongs to A, but f of 4 does not exist. There is no output related in B for 4, so this is not a function. Now for F3, we have 1A, 2V, 2C, 3A, and 4B. And so what happened with this one is that it's not a function because the input 2 is related with two different outputs. So 2 is related to B, but 2 is related to C. So we have that f of 2 is B, but at the same time, also f of 2 is C. And we cannot have that going on with functions. So in this particular case, it is not. So for f of 4, notice that we have 1 going to B, 2 going to B, 3 going to B, and 4 going to B. This is a constant function, but that works. This is a function. Every input has one output, even if it's the same output. Now let's move on to question number 4. This asking for arrow diagrams for each of the following relationship and then realize if this is a function or not. So you can go with PQR, and then you do 1, 2, and then here you're sending P to 1, you're sending Q to 2, and you're sending R to 1. This holds the fact that every input has one output, so this is a function. Okay. Now for the second relationship, we have PQR being sent to 1, 2 once again, but we have P being sent to 1 and P being sent to 2. Q being sent to 1, and R being sent to 2. The big problem here is that P has two different outputs, so this is not a function. Now, C, which is P being sent to 1, this is PQR, and then we have 1, 2, and so we send P to 1, we send Q to 1, and so the big problem here is that R doesn't have an image. So this is not a function. Okay, that's exactly the problem in here. Now, question number 5 talks about consider the relationship G from R to R defined by xy belonging to G means that y is equals x squared. Is G a function? What is G of 3? What is G of minus 2? Those kind of stuff. So as a function, yeah, G is a function, since for every real number, you're using the relationship y is equals x squared. So in this case, yes, this is a function. From R to R, that's going to work out well. Now, what is G of 3 and G minus 2? Well, G of 3 is just 3 squared, which is 9. And G of minus 2 is just going to be 4, which is fine. So this will work out well. The function notation for what we usually will do is G of x is equals x squared, which is also y is equals x squared. This is completely valid. So for those of two things, we have that this is a function. Now moving on, question number 6. We're considering the relationship of the unit circle. We have spoken quite a bit about the unit circle. And just a reminder here, this unit circle is likely not going to give me a function. Why? Because we have multiple, the same input is going to give me multiple outputs. So 0, 1 also matches with 0, minus 1. So you have these two things for the circle, since when x is equals 0, we get y squared equals 1. And that's going to give me as an answer y equals 1 or y minus 1. So it's not a function. The relationship is a circle. We know that from before. And both 0, 1 and 1, 0 are part of the circle, because when you do 0 squared plus 1 squared, you get 1. You also get 1 squared plus 0 squared being 1. So they belong both to the circle. Now, in question 7, we have the set A being 1, 2, the set B being x, y. how many different relationships are from A to B? And well, because we have many ways of doing this, we can check how many subsets do we have for an AB. And so the set AB has the 1x, 1y, and we also have the 2x, and we have the 2y. So this is, it has 4 order pairs, right? So the cardinality, or the number of elements of A times B is 4. So the many different subsets that we have is like we're talking about what are the cardinality of the set parts, or how many total subsets can we have forming with this. And that's going to be 2 to the 4, which is going to be 16. These are all the possible combinations, all the possible sets. Part is, it will be all the possible subsets that you can get from this. So you can get the empty relationship, you can get A times B, but you can also get things like only the set of 1x, only the set of 1y, so on and so forth. All the possible subsets that are in here. So now, how many of these functions are going to be relationships? And the thing is, like, now this is a different thing, is how many from B going to A are we going to have? So this is like B power A, which will be like 2 to the 2. And so this is going to be 4 here. So we're going to have 4 functions that are possible, where we're just covering things that are going from A to B, and they have they're covering all the inputs and all the outputs. So if we're covering all the inputs and all the outputs, means that you're gonna have, if you have 1x, you also have to have something with 2. 2 gotta go to somewhere. So that's why we're restricting, and we have a less quantity of elements in here. Those 4 functions, let's list all those functions. We have the 1x, and then we have the 2x, where we can send both of them to x. We can have also the 1x, and now let's send 2 to different things. Let's send 2 to y. We can also send 1 to y and 2 to x. And we can send 1 to y and then 2 to y too. And those are going to be all the possible functions that we're going to have from here. Now, moving on, for each of this, let's determine if there are a function or not. So we're going to assume that this is going from R to R. And so from R to R, 3x minus 7 is fine. If we plug any number on R, this is going to give me a real number. So this is a function. Now, with square root of x, it's not going to be a function from R to R, because I cannot take negative numbers. So a square root of x belongs to the real numbers only if x is positive. So if we're taking numbers from the reals that are negative, this is not going to give me an image. And so not all the elements have an image for this, and it's not a function. Now, h of x being plus or minus a square root of x is not a function anyway, because it's giving me both values. It's giving me plus the square root of x, and it's giving me minus the square root of x. For a single value, it's giving me 2 outputs, so it's not a function. Now, k defined by x, y belongs to k if y is less than x. This is a weird condition. And for a given x, there's going to be many different values of y less than x. And so this is, the output's not going to be unique. So it's not a function. Now for number 9, we want to say if this is true or false. Every function is a relation. This is true. Every relation is a function. This is false. We just saw that functions are very specific relationships. If f from a and b is a function and f of 2 is 5, then 2, 5 belongs to f. Yes, this is by definition. What is 2 to 5 belonging to the relationship, 2 is the input, 5 is the output. A function can have two different outputs for the same input. This is false. One of the conditions of being a function is that it can only have one input. Now, two different inputs can produce the same output. This is true. We have the constant function in particular where you can send different inputs to the same output. Now, question 10. Let's be a, b, c, and t equals 1 to 3. Let's define a relationship from s to t that is not a function. And so one of the things that's going to happen here is that you can have many different relationships. So if you're doing this, you can get different things. So don't worry if you're getting different things, because you can get different, completely different things here. So just for example, if I want to define a relationship that is not a function, one of the conditions of functions is that I need everything to have an output. And if I just do, let's say, A1, B2, and that's it, and I close it there, and I don't give an if I don't give an output to C, then this is a relationship because it's a subset of the Cartesian product, but it's not a function. Now, B, define a relation from S to T that is not a function because some element of S is related to more than one element of T. So again, multiple ways of doing this, but you can do always A to 1, and you can also do A to 2. And this already is a relationship, but it's not a function. Now, define a function from S to T where not every element of T is used as an output. Once again, we can go with the constant function. We can go with A to 1. We can go with B to 1. We can go with C to 1. So notice that we're sending everyone to 1, which is fine for a function, as long as everything has an output and they have, and then not being sent to different places. The same input's not sent to different places. Now, for number 11, we have a very specific function that is sending 1 to 3 to A, B, C, D, and is given by 1 to B, 2 to A, and 3 to B. So we want to recognize what is f of 1, what is f of 3, and according to this relationship, f of 1 is B, and f of 3 is also B. We want to recognize that the domain is the 1 to 3, and the codomain is the A, B, C, D. Okay? It's very important to understand where are the domain and codomain in a function. Now, last, which of the elements of the codomain are hit by f? So we're talking about which are the outputs really. And so the outputs are just really A and B, because we have A and B here. And we don't not use our C and D. Okay? So with this, we get to the end of the examples for section 1.3.